Hi, my name is Marcus.
And I'm Ernestas.
We're third year students from the Camel School of Mines, University of Exeter. We're here in Carboneras, sunny Spain, right on the seafront. Our hotel where we're staying is literally behind us there. There's actually some students getting on with a regional geological synthesis as we speak behind us. And this trip is really kind of a culmination of the 3 years we spent at CSM, Camel School of Mines, so far. We've got the 3 different courses here, so there's the pure geology, applied geology, and then engineering geology and geotechnics as well. And one of the really nice things about this trip is it's a chance for us to all be together. We're all staying at the same apartment. Some of the tasks we all do together, but it's also a chance for us to split up into our different specialities and work on the more specific modules that we've been working on. So for example, be that mineral exploration and resource estimation, environmental land remediation, or some kind of geotechnical assessments and stability analysis as well.
The reason we've come to this specific area of Spain, the Betic Cordillera, is to look at world-class exposure of metamorphic, igneous and sedimentary rocks. There is also some really interesting abandoned gold mines, as well as some really great evidence of tectonic activity.
As well as the obvious geological aspects of the trip, we've also made this little accompanying video showcasing some of the field localities and some of the fun we get up to here at CSM, showing you a bit of what we're about. So yeah, we hope you enjoy.
So we're here at Mesa Roldan in Carboneras, just south of Carboneras, and Mesa Roldan is an extinct volcano. So it would have been a seamount in the sort of Neogene, starting in the Teutonian and into the Messinian. And what we're seeing here on the flanks of the volcano is a succession here of volcanoclastic sediments. So these have volcanic debris, so mainly boulders and rocks in mainly a carbonate matrix. So what the students are doing here is that they're logging the sediments and making observations on the nature of the sediments in this particular section. And as they're going along, they're recording the differences that they see in the different sediments in the succession here to try and work out the specific episodes that happened here. We look at the rocks in this section here, we can see that there's distinct differences in the clast size. They're all fairly rounded, so there's obviously been some transport going on in this succession here. The matrix appears to be dominated by carbonates, a fairly fine carbonate mud with some trace fossils in it, but the succession essentially is indicating that the volcanic material is sort of being reworked from the volcano down the slopes into a sedimentary basin where this carbonate mud is precipitating. They're worked into these distinct beds, of course, and fine-grained or finer-grained material.
Okay, so here we are at the top of Mesa Roldan. We've walked up through a whole succession of volcanoclastics, and now we've reached the top, and we're in something which obviously is very, very different. What the students and myself have found up here is basically a whole stack of disaggregated small shell material as well as larger shell material. A lot of that shell material looks like it's been very happy living in high energy environments, but then it's been washed off what was probably a reef top and down to form these extensive beds that we see behind us. It's currently very difficult from one locality to just figure out exactly where we are within a reef setting, but as we've come up onto our seamount, we've obviously got a complex patchwork of different environments. And one of the interesting features we can see in the cliffs behind us here is actually a line of clasts that are now being displayed as small voids in there, which are actually volcanoclastic bombs. And beside that, we see a whole series of beds of further bioclastic materials. So we're obviously seeing an interaction of these volcanoclastic and then carbonate reef environments.
Megan's drawn a quick diagram just showing what we think is going on. So when we look at the actual rock especially sort of in this region up here, and look at mineralogy, we see unusually lots of garnets in it, as you know. So we also saw related garnets, garnet mica schists preserved as sort of, we think of these xenocrysts within the actual rock itself, as we've got an example of. And these in the rock have sort of melted margins, and the larger clumps sort of preserved, but as you get into smaller pieces of this, they're almost melted completely. And we think that the actual garnets we're seeing in a lot of the volcanic rocks are actually derived from the garnets left behind sort of in here, where most of the rock's been melted, but for some reason the garnets are still stable and so preserved and left in the melt, which has then been erupted and formed the rocks around us today.
Well, hello everyone. I'm going to be talking about the Messinian salinity crisis today. Generally, it was about a 60-metre change in sea level associated with it. It's thought to be uplift associated as well. Thought to be due to the westward rollback of a subducted Tethys Ocean lithosphere along with associated asthenosphere upwelling.
So this first section here, some of you may have noticed that the laminae and the mudstones were being pushed down by the gypsum crystals. And it's because during diagenesis the mud sediments are more, can be deformed.
Hi man, we're digesting.
Hiya, I'm Patrick, and this is gypsum deposits which happened during the Messinian salinity crisis. Basically, Africa and Spain moved into each other, and the Strait of Gibraltar closed, and it caused a lot of evaporation and a lot of precipitation of salt, and eventually gypsum. And which these big massive crystals which have occurred just at the bottom of a big sedimentary unit. And, yeah, it's pretty impressive looking.
Disperse or put that down into the settling ponds that are over there, which now forms part of the botanical garden. Okay, so materials would settle and probably at regular intervals be dug down and put down into the waste dumps. So that's a continuous process of how you're getting ore out in this particular case. In order to do the processing, you need about 1 kilogram of cyanide per ton of ore. it's by using zinc. So adding zinc to the solution gives a simple replacement within the cyanide so that you get a zinc taken into solution, and that causes precipitation of gold and silver. So it's filtration of that liquid afterwards means you can recover the gold and silver. So that's sort of a crude outline of what the processing is like.
Where we get our samples of the clay that we're going to test the moisture content in. First of all, we take it over to the corner here. We'll crush it down in pestle and mortar. It's further crushed down by another pestle and mortar, and then it enters into the sieve. The sieve has holes of 0.63 millimeters, so it's very fine. Right, after sieved, you will weigh it with the scales.
Keep it over because you don't want to lose it. Because what you'll notice is,
and you'll try to get around 40 grams of clay.
Yeah.
And what you want is to add about 10% water at a time, so 4 grams or so.